Welcome back to our lesson in chapter 2. Let's talk about the basic concepts of derivatives and their applications. We are now in section 2.3, which is entitled Differentiability and Continuity of Functions. So we have the following learning objectives. Number 1 is to determine if a function is differentiable at a point in real number. Then determine the discontinuity of a function at a point based on its non-differentiability at that point. And lastly is to analyze whether a function is differentiable or not over a particular interval. And we need the following prior knowledge. Number 1, we must have a knowledge about the continuity of functions. Then we must have a knowledge about simplification of algebraic expression. Lastly, we must have the knowledge about evaluation of limits. So whenever limits are discussed, the concept of continuity is not far behind. So in this section, the relationship of the continuity or discontinuity of a functions with the existence or non-existence of their derivatives at a point and over intervals will be tackled. So that will be our focus in this lesson. So remember that there are three requirements of continuity of a function at a point C and f of c, as discussed in our previous chapter. That is, a function f is continuous at a point C, f of c, if it satisfies all of the following conditions. So we have three conditions. Number 1, limit of f of x as x approaches c exists. So there is a limit, or the value of the limit is a real number. And number 2, if f of c exists, and the most important part is the limit of f of x as x approaches c is equal to our f of c. So that is the most important one. So this number 1, number 2, number 3 must be satisfied before we can conclude that there is a continuity of a function at a point c or f of c. So the following theorem relates continuity with differentiability. So which is state when a function has a derivative or when its derivative exists. So talking about differentiability talks about the state when a function has a derivative. So that is the essence. Or when its derivative exists. So to make it formal, we have theorem 2.3.1. Differentiability implies continuity. When, if a function is differentiable at a point, then it is also continuous at that point. So take note, if a function is differentiable at a point, so this is the f, then it is also continuous at that point. So logic tells us that since theorem 2.3.1 is an f-then statement, so we have the f, then we have the then. It means that is contrapositive. So it means that its contrapositive is also true. It is stated in the following corollary. So we have corollary 2.3.1, the contrapositive of theorem 2.3.1. States that if a function is discontinuous at a point, then it is not differentiable at that point. Pag discontinuous siya sa point, then it is not differentiable at that point. So we have an example. Consider the quadratic function given by f of x is equal to x squared minus 2x. So using the limit theorem, the previous topic, we get the derivative of x, f prime of x is equal to 2x minus 2. So take note, in algebra, this is a linear. So the derivative of function is a linear. Meaning yung exponent ng variable is 1. Pag 2, that is quadratic. So stated here, we have quadratic functions. Since this is a linear function, it is defined for any real number. So this means that the original function f is what? Differentiable for any real number. Or in fact, differentiable in its domain. Thus, by theorem 2.3.1, the given function is continuous at any particular number included in its domain. So, pwede siya sabisan nun sa nga number, even its domain. So, for example, if this is the value of x is 1, so pwede siya. Okay? If this is 2, pwede. So, the given function is continuous at any particular number, including in its domain. So, that is our example number 1. For number 2, finding the derivative of y is equal to f of x is equal to 1 over 2 minus x using the limit definition on our previous topic. We get the derivative of x, or f prime of x, is equal to 1 over the square of 2 minus x. So, by choosing the value of 3, for example, in the domain of f, we can say that the derivative is defined, and we have f prime of 3, or the derivative of the function at point 3 is equal to 1. Thus, the function is differentiable at x is equal to 3. Okay? So, by theorem 2.3.1, the function is continuous at 3. In fact, we can check that for all values in the domain of the rational function, the function is differentiable. So, the only real number for which the function is not differentiable is what? If x is equal to 2, y. So, if you're going to substitute 2 here, so 2 minus 2, it becomes 0. The square of 0 is 0. So, we get the limit does not exist. So that is not differentiable. So, according to our theorem, if that is continuous, that is differentiable. If it is not continuous, or there is a discontinuity, so that is not indifferentiable. So we have here this state that is not differentiable if our x is equal to 2. And 2 is not part of the domain of f. The function is not defined at 2. So f is what? Discontinuous at x equals 2. Right? So comparing example number 1 and example number 2, we can say that here there is a point in which we can say that there is a not differentiable. But in example number 1, in a linear status of the derivative of the function, you can say that all, or at any particular number, the given function is continuous, even in its domain. So that is the difference. Now, here, this is the graph of our second example. F of x is equal to 1 over 2 minus x. So as you observe in this part, may 2. So we can see there is a discontinuity. So note the last part of example 2 should not be interpreted to mean that the non-differentiability of f made it discontinuous at 2. So dili na to i-interpret nga ang pagka non-differentiability of f mao'y naka-discontinuity or naka-discontinue sa 2. Bagkos, according to our corollary, that the discontinuity at 2 makes the function not differentiable at 2. So, ang discontinuity mo'y nakapahimo not differentiable siya at 2. So, we have another example. Example number 3. Consider the piecewise function. F of x is equal to x squared if x is not equal to 0. Then f of x is equal to 1 if x is equal to 0. Determine if the function is differentiable at 0. So here, this is our 0. We have this one, f of x is equal to 1. So let's try if the given function is differentiable at 0. So first, we will apply the limit theorem. The derivative of the function f at 0, right, is equal to limit f of a minus h minus f of a all over h. As our h approaches to 0. So here we have our a 0, so we get limit f of 0 minus h minus f of 0 all over h as our h approaches 0. So here is equal to f limit. So remaining here is negative h minus, if our f is equal to 0, so we have this one, x is equal to 0, so we have 1 here. All over h as our h approaches 0. So using our limit, since that this approaches 0, so that is not, doesn't mean that it is equal to 0, so we are going to use our x squared here. So is equal to limit to x squared, right? So that is negative h. The square of negative h minus 1 over h as our h approaches 0. So we have limit of h squared minus 1 over h as our h approaches to 0. Okay, so equals, we have 0 minus 1, and then we get 0. So this negative 1 over 0. Okay, so applying the lesson in our previous chapter, so we need to get on what sides of 0 if there is a limit existed. So to result ani, we can have the positive infinity or the negative infinity. So we will try at the right side. So we got equals limit of h squared minus 1 over h as our h approaches 0 from the right. So we got negative 1 over 0 from the right. So according to our theorem in our previous lesson, if the number in the numerator is less than 0, and then if our denominator is 0 from the right, or from the right of 0, so we get negative infinity. Pag dili sila kapareha og direction, so this is less than 0 and this is greater than 0, so we have negative infinity. So if we are going to try limit of h squared minus 1 over h as our h approaches 0 from the left, so we got still negative 1 and then 0 from the left, so that is positive infinity. We can see that from the right we got negative infinity, from the left we have positive infinity. So therefore, the limit of h squared minus 1 over h as our h approaches 0 from the right is that equal to the limit of h squared minus 1 over h as our h approaches 0 from the left. So therefore, it is clear that they are not differentiable at 0. Since they have different limits, so the limit does not exist. So they are not differentiable. So the function is not differentiable at 0. Remark that the previous solution is not technically incorrect, but you may find this process rather lengthy. So taas lang siya nga process, but you can make it simpler. You can apply the corollary 2.3.1 in the solution. Note that the function fails to be continuous at 0. Diba? Although both f of 0 is equal to 1 and the limit of f of x as x approaches to 0, there is a limit here which is 0. So natay result for our f of 0, natay result sa atong limit, but the problem now is they are different. So therefore, the third condition, meaning they are not, there is no limit, so that this does not exist. So their different values means that f discontinuous at 0. So by corollary 2.3.1, the function is not differentiable at 0. So we can use either the first one or this simpler technique using the corollary. So logic lang ato gamitan para mas madali nato pagkuha ang answer. So proceed to examine when the function is differentiable over an interval. So now we are going to talk about interval. So we are done with the point. So especially those containing 1 or 2 endpoints, there is a need to introduce the one-sided derivatives. A one-sided derivative is either a left-hand or a right-hand derivative. So this is our definition 2.3.1, left-hand and right-hand derivatives of a function. So the right-hand derivative of a function f at a point C is given by the right-hand derivative of a function f at a point C is equal to the limit of f times the quantity of C plus h minus f of C all over h as our h approaches 0 from the right, if this limit exists. The left-hand derivative of a function f at a point C is given by left-hand derivative of a function f at a point C is equal to the limit of f times the quantity of C plus h minus f of C all over h as our h approaches 0 from the left, if this limit exists. So take note, these two formulas, they are only differ on the symbol. We have the right and we have the left for the negative one. So the other parts of the formula, they are the same. Example, consider the function given by f of x is equal to 2x squared if our x is greater than or equal to 1. And then f of x is equal to 4x minus 2 if our x is less than 1. So determine the derivative of the function, determine the right hand derivative of a function f at a point 1 and determine the left hand derivative of a function f at a point 1. So we need to apply the given formulas. So the first one is the right hand derivative of functions f at a point C. So sa gamiton nato ating duha, so we have this one, the right hand meaning greater than 1. So we have x is greater than or equal to 1. So we can use 2x squared. Okay? So right hand derivative of a function f at a point 1 is equal to limit of f times C plus h minus f of C all over h as our h approaches 0 from the right. Alright, equals. So we got limit. Yung C, pulihan na to og 1. Approaches 0 from the right. Equals. So we have from the right, so we are going to use 2x squared. So limit 2. So x squared, so we get 1 plus h, the square of 1 plus h, minus f of 1. So 2 times square of 1 over h as our h approaches 0 from the right is equal to limit. So the square of 1 plus h, so we get 1 plus h. 1 plus h plus h plus h squared. So we get 1 plus 2h plus h squared. So we get this 2 times h squared plus 2h plus 1 minus 2. Right? 1 squared is 1, 2 times 1 is 2 over h. As our h approaches 0 from the right. Proceed. We got limit 2h squared plus 4h plus 2 minus 2 all over h as our h approaches 0 from the right equals limit. So we have 2 minus 2. So remaining is 2. H squared plus 4h over h as our h approaches 0 from the right. So we have the common here, which is h. So 2h plus 4 na lang. Okay, cancel na to ang h. So the remaining as limit of 2h plus 4 as our h approaches 0 from the right. So the remaining limit is, the answer is 4. Next, the left-hand derivative of function f at the point 1 was limit f times the quantity of c plus h minus f of c over h as our h approaches 0 from the left. So this is from the left, so we're going to use the second one, that is less than 1. So we are going to use 4x minus 1. So applying the same method, we can arrive here. Diba 1 lang? So f of 1 over h as our h approaches 0 from the left. So atong gamitan is ang ikaduha, 4x minus 2. So 4 times 1 plus h minus 2 minus 4 times 1 minus 2. As our h approaches 0 from the left. Next, limit. So here we got 4 plus 4h minus 2. Then here 4 minus 2 is 2. So minus 2 over h as our h approaches 0 from the left. So we got here negative 4 2, tapos 4. So ang remaining na lang is limit of 4h over h as our h approaches 0 from the left. So we can cancel this one, so the remaining is 4. So the limit of 4 as h approaches 0 from the left is 4. So as you observe, they have the same result. Therefore, we can say that they are differentiable. So there's a limit exists. So differentiable siya from the left and from the right. So we have this theorem 2.3.2, existence of the derivative at a point x equals c. So take note, if for a function f, it can be shown that the right-hand derivative of a function f at point c is equal to the limit or the left-hand derivative of a function f at point c, then the derivative of c exists. So meaning, pag ang result sa derivative sa c from the right hand and left hand is the same, so there is an existing derivative of that point c. So it follows that f of x is differentiable at the point c, f of c. So as you observe, kapareha siya og mga condition sa previous na to lessons with regards to the existing limits. Nga pag ang limit sa right hand o left hand kapareha, so there is a limit existed. Example number 5. Consider the function given by y is equal to f of x is equal to 3x minus 2 if x is greater than or equal to 1, and then f of x is equal to x squared plus x if x is less than 1. Compute for the right-hand derivative of function f at point 1 and left-hand derivative of function f at point 1 and determine if f is differentiable at 1. So here first, the right-hand derivative of a function f at point 1 is equal to limit of f times c plus h minus f of c over h as our h approaches 0 from the right. Substitute ang value sa c, which is 1. So we get limit f of 1 plus h minus f, tapos yung c is 1, over h as h approaches 0 from the right. So apply. So since that is from the right of 1, so we need to use 3x minus 2. So limit, so 3, pulihan na to ang x og 1 plus h minus 2, tapos minus. So ang x pulihan na to og 1 all over h as our h approaches 0 from the right equals limit. So we get 3 plus 3h minus 2. Here, 3 times 1, 3 minus 2, 1. So we get negative 1 over h as our h approaches 0 from the right. So 3 og negative 2 minus 1 is negative 3. Tanggalan na lang na to. So we get limit 3h over h as our h approaches 0 from the right. So cancel to h. So the limit of 3 as h approaches 0 from the right is 3. Now let's go to the left-hand derivative of function f at point 1. We got the derivative of function f, the left-hand derivative of function f at point 1. So we got limit of f times c plus h minus f of c over h as our h approaches 0 from the left. So we get here limit of f times rc is 1, so 1 plus h minus f of 1 all over h as our h approaches 0 from the left. So since we have from the left of 1, so we are going to use x squared plus x for this 1, so 1 plus h. So we get limit of our x, pulihan na to 1 plus 1, 1 plus h, the square of 1 plus h, plus 1 plus h. And then minus f of 1. So here, instead of x squared plus x, we are going to use our f is equal to 1, so we have 3x minus 2. So we got 3 times 1 minus 2 all over h as our h approaches 0 from the left. So proceed, limit. So here we have h squared plus 2h plus 1 plus 1 plus h minus, so 3 times 1, 3 minus 2, 1, so minus 1 all over h as our h approaches 0 from the left. So is equal to limit. So 1 plus 1, 2 h squared plus tatlo na yung h, 2h plus h, 3h. 1 plus 1, 2 minus 1 1 over h as our h approaches 0 from the left. So equals. So we cannot factor this one. Substitute na lang to ang value sa h, which is 0. So we got remaining here 0, 3 times 0. So we have 1 over 0. So to check that one, we got 1 over using the previous learnings in our previous chapter. So that is 0 from the right equals positive infinity. So here, since we have 3 and positive infinity, they are not equal. So therefore, the given function is not differentiable at point 1. So we have the next definition, 2.3.2. A function is said to be differentiable on an open interval if its derivative exists at every number in A and B. So take note, in terms of interval, open interval, a function is said to be differentiable if its derivative exists at every number. Meaning, from point A to point B, lahat ng number, even in between, dapat derivative. Nag-i-exist ang derivative, ana. So example, this is the illustration. The function f of x is equal to 2x over x minus 1. So, is differentiable on the interval 2, 5. Since the point of discontinuity of f Sa any number in between 2 and 5, substitute mo dira, okay lang siya. Right? So, for example, 2. So, substitute mo dira 2. So, we have 4 over 1. Right? So, 3 and so on. But, when our x is equal to 1, hindi siya pwede. Kaya it will become 0 ang denominator. So, there is a discontinuity. Right? So, in the given interval 2, open interval 2, 5, okay, so yeah, that is differentiable. And the same function, the first example, dili siya pwede sa open interval negative 2 and 3. Why? Because 1 is an element of negative 2 and 3. So, in the open interval negative 2 and 3, sa included na negative 2, negative 1, 0, 1, 2, and 3. Included si 1. So, dili siya pwede. Therefore, f is not differentiable on the interval negative 2 and 3, given in this function. So, take note this following remarks. In most books, so the following are stated as theorem. Letter A, any polynomial function is differentiable on open interval negative infinity and positive infinity or any of its subset. Take note, this is a polynomial function. A specific example will be the f of x is equal to x squared. Ang iyang derivative is 2x. So, this is a linear, therefore, it can be defined everywhere, implying the derivative of f exists on the real number. Next, rational function is differentiable in its domain or any subsets. So, this means that a function is differentiable at any subset of intervals of the domain which does not contain the point of discontinuity. Pwede siya differentiable basta way labot ang point of discontinuity. So, the same function will be continuous in the intervals negative 5, 0. So, for example, to our illustration 2.3.2. Basta lang way labot ang point na naadi ang discontinuity. Now, for letter C, the square root function. So, f of x is equal to the square root of x is continuous on half-closed interval 0 and positive infinity. However, it fails to be differentiable on the same interval since the left hand derivative of function f at 0 does not exist. So, meaning, yung lower pa ni we have negative 1, dili na siya pwede. Okay, for example, negative 1, square root negative 1, that is I, that is imaginary. That is not a part of the real number system. So, the said function is differentiable for any interval that is subset of 0 and positive infinity. Okay, but less than 0, dili na siya pwede. And the last one is the absolute value function. F of x is equal to absolute value of x is equal to x if x is greater than or equal to 0. Negative x naman pag ang x na to is less than 0. And take note, our absolute value is differentiable only on the open interval 0 and positive infinity or its subset. Pwede sad og negative infinity and 0 or its subsets. And that's all for our topic. This time talks about differentiability and continuity of a functions.